Okay, moving on to polynomials, zeros of polynomials. And what we're after eventually here is graphing general polynomials as opposed to just graphing quadratics. I'll be able to graph. Did we do that already? Looks like the next thing will be rational functions. Maybe we already worked with graphing polynomials in the last video. Well, anyways, we're looking for the zeros of polynomials, basically where they hit the x-axis. So 2.5 zeros of polynomials. And I don't know, waiting for my webcam is not focusing. Focus, please. May work. Oh, good. A lot of good that did me. So anyways, we begin with what's called the zero factor theorem. And what is that? Well, it's going to give us, well, sorry, it's a rational zero theorem. So if there are rational roots, like, counting numbers or fractions, non-radical numbers, like radical 2 isn't rational, okay? But for all other kind of solutions that are rational, we have a theorem that will tell us the possibilities. So there's only a finite list of possible answers for zeros, or places where these polynomials hit the x-axis. So possible rational zeros. I'll just write possible zeros for the sake of sanity. And the numerator, what we're going to do is put the factors of the last term, which in our notation would have been a sub 0. And then in the denominator, we're going to put the factors of the leading coefficient, which in our notation is a sub n. So I don't want to, well, I guess I'm going to have to, right? So the polynomial form, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus ax plus a sub 1x plus a sub 0. Okay, so it's that thing. That's what these a sub 0s and a sub n's are. Okay, so looking at the book, what they're dealing with, you have this big ugly polynomial, so x cubed plus 3x squared minus 6x minus 8. And then you're going to use this theorem to figure out what are the possible solutions. If you set this equal to 0, what would be the possible rational solutions? So not just all solutions, but just the rationals, right? So how do I figure this out? Well, you put the factors of the last guy in the top, and with regards to signs, you're always going to put plus or minus in there. Because, for example, the number 5 can be divided by 5, but also negative 5. And likewise, the number negative 10 can be divided by 10, but also negative 10. So we're going to put plus or minus on each one of the factors. So for negative 8, it's plus or minus 1. 1 divides 8. And then plus or minus 2. And then plus or minus 4. That's as good as it gets, right? And then plus or minus 8. And the denominator, the only thing that divides the leading coefficient is just 1. So you'll put plus or minus 1. And then we'll simplify that, right? So plus or minus 1 over plus or minus 1 is just plus or minus 1. And then plus or minus 2 over plus or minus 2 will just give you plus or minus 2, etc. So it's a finite list. It's kind of a long list, right? So we have 8 numbers we would have to go through and check manually. But it's better than, just going out into the middle of the desert and wandering around for a couple of years. Right? So anyhow, here's number 6. We have f of x equals 3x to the 4th minus 11x cubed minus 3x squared minus 6x plus 8. Okay, so let's try this again. The possible zeros, so this is about the same for the numerator again. So did I write the same polynomial? No. the last term plus or minus 1, plus or minus 2, plus or minus 4, same deal. Plus or minus 8. In the denominator, then you're looking at factors of 3, so plus or minus 1 or plus or minus 3. So this time, sorry, I went off the page there. This time we get all the rational zeros from the previous guy, so plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. But then we're also going to get these fractional terms. So plus or minus 1 over plus or minus 3 will give you plus or minus 1/3, and then you'll have plus or minus 2/3, and then you'll have plus or minus 4/3, and then plus or minus 8/3. Okay, so this time the list is a lot longer. And you would have more work to do if you wanted to figure out which works. So finding out which works then is the next step. So section 2, finding the zeros, right? So we have this list, and now we actually want to investigate the list and determine which works. Okay, so the book is going to advise doing trial and error. So you literally just go through and randomly pick zeros, and then long division. But not long division in the traditional sense. I mean synthetic division. Okay. So basically, you'll divide out the polynomial by x minus the possible 0, and then if your remainder term is 0, that means it's divided. It can be divided evenly by the particular number. So let's look at number 10. We have f of x equals x cubed minus 2x squared minus 11x plus 12. Okay, so our possible zeros then, we'll have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, geez, plus or minus 6, plus or minus 12. And that will be all over plus or minus, I guess, just 1. So our zeros then 1, 2, 3, 4, 6, 12. And, you know, there's no magic to guessing which will work. You just start at the beginning. So start with 1. And so you'll have 1 right here. And you'll do synthetic division. So 1, negative 2, negative 11, and then 12. So bring down the 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. 1 times negative 1 is negative 1. Negative 11 plus negative 1 is negative 12. 1 times negative 12 is negative 12. Oh, and we got super duper lucky, right? So this one is a 0 of the polynomial. And generally you won't stop there, right? So we have x minus 1, but then this guy right here is x squared minus x minus 12, and you can set that equal to 0 and solve for its zeros, and that will give you the remaining zeros. So right now, certainly we have 1 as a 0, but there's more, okay? So what's happened is that we've effectively taken this polynomial and factored it into x minus 1 times x squared minus x minus 12. And then what we do is just factor this character, and hopefully that will give us the rest of the zeros. So x minus 1 times x minus 4 times x plus 3 is 0. So the other zeros in addition to 1 then will be 4 and negative 3. So what you're really doing is just looking for 1 0, and then the other zeros will kind of fall out of the synthetic division. Okay. Okay, so let's continue on then with another one. Here's 14. And we have f of x equaling 2x cubed plus x squared minus 3x plus 1. Okay, so the potential zeros we're looking at from the constant term, plus or minus 1, and then all over plus or minus 1, plus or minus 2. Okay, so we'll have plus or minus 1, and then plus or minus 1/2 for our potential zeros. So, go through and try them. So try 1. So we have 2, 1, -3, 1. Another 2, 2, 3, 3, 0, 0, 1. So that didn't work. This is not, that has to be a 0 right there for it to work. So try -1. So 2 comes down, -2 is -1, 1, -2, +3. No, that don't work. Okay, so we have to go to the fraction. Let's try 1/2. Bring down the 2, you get 1, 2, you get, really, 1 again. And then it's -2, and then 1/2 times -2 is -1. So we got our first 0. And then the rest of it, we have 2x squared plus 2x minus 2 is 0. And we could try to factor that. But you're going to have, issues right there. You can factor out a 2, so you'll have 2 times x minus 1/2 times x squared plus 2x, x squared plus x minus 1. Then you try to factor this, right? So you're not going to be able to do it by hand. You're going to have to go to the quadratic formula. So x equals plus or minus, x equals negative b, it's just 1, plus or minus the square root of b squared, so 1 minus 4 times a times c. That'll be all over 2a, which is just 2. So we have -1 plus or minus square root of 1 plus 4 is 5 all over 2. And then we have that equaling to, those are they, right? Those are our 2 zeros, and we're done. So our zeros then, in this case, we have 1 rational 0. So what did we decide that was? 1/2. And then we have 2 irrational zeros. So -1 plus radical 5 over 2, and then -1 minus radical 5 over 2. And that'd be it. Okay, so I think sort of intuitively we've been using these next theorems, the fundamental theorem of arithmetic and the linear factorization theorem. We'll just sort of state these guys. So the fundamental theorem of arithmetic, basically if you have a function and its degree is greater than or equal to 1, it has at least one complex solution. Okay. So what did I say? If your polynomial p of x has degree n greater than or equal to 1, then p of x has at least one complex root. Okay. From there, we go to the linear factorization theorem, which basically just says you can break any polynomial down into a product of binomials. Okay. So linear factorization theorem. What do we do? If you have this general form of a polynomial, so if p of x equals a sub n x sub n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2, x to the n minus 2, plus dot dot dot, plus a sub 2 x squared, plus a sub 1 x, plus a sub 0. Then you can always rewrite it as a product of a bunch of binomials. Okay, so it would be a sub n times x minus c1 times x minus c2 times x minus c3 dot 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 all the way times x minus c sub n. Okay, so there will be n of those things, and the c sub n may be complex. Okay, so and we'll just note c sub n are complex. And when we say complex, we actually mean that they can be real, right? So a complex number is real when the imaginary part is 0. So we'll just note possibly real. And they don't have to all be different. Okay? You can have repeated roots. So that's what they mean when they say possibly not all distinct. Okay, so we'll look at one of their exercises associated with this issue. And I believe what they're having you do is kind of make up a polynomial based off some information. So they want you to find a third degree polynomial with real coefficients that has -3 and I as 0. And f of 1 equals 8. Okay, so one thing that I didn't notice, that I didn't note, which the book probably notes, is imaginary are these, these complex roots that are imaginary always appear in conjugates. So in particular, our form for our polynomial p of x, you'll have some leading coefficient, basically to be named later, and then you'll have from the -3 x minus -3, and then from the I you'll have x minus I, but because these imaginary guys always appear with their conjugates, you'll also have x plus I. If that were not the case, your polynomial would have imaginary terms in it, and we're not dealing with that. If you remember our definition of the polynomial, which maybe I should have made a bigger deal out of it in the beginning, right here, these a sub n terms are all supposed to be real. Okay, we don't play around with imaginary coefficients. So in order to procure that arrangement, we have to have these conjugates. Okay, so we're going to want to multiply this out and get it into the more standard form of a polynomial. And so let's take a look at how that is. Well, first maybe we should figure out what this a is. I think it'll be a little more easier. So if you plug 1 into this formula, the output is going to be 8. So it'll be a times 1 minus -3 is 1 plus 3, and then 1 minus I, and then 1 plus I. Okay. So let's multiply out the conjugates first. 1 plus 3 is 4. And then, so first 1 times 1, the outer I, the inner negative I cancel, and then last minus I squared, which we can replace I squared with -1. So 8 is a times 4 times 1 minus -1 is 1 plus 1, that's 2. Okay, so we get 8 equals 8a, and then of course a is just equal to 1. So our polynomial p of x is going to be a, which is 1, times x plus 3 times x minus I times x plus I. The book wants you to put it into the sort of the standard form of a polynomial, so we're not going to leave it like that. We're going to go ahead and FOIL everything out. So let's start with the conjugate pair. So first, we'll give you x squared, the outer I, inner negative ix, those will add away, and then net minus I squared. And of course, I squared is negative 1, and then minus 1 will be plus 1, and you get x squared plus 1. Okay. Back in algebra, pre-algebra, you would see these things and we call them prime. But now, hopefully, you can appreciate, well, these aren't really unfactorable. The theorems we were just looking at say it's always going to be factorable into a product of binomials, just you have to include imaginary numbers in order to pull that off. So anyhow, go ahead and FOIL the rest out. So you get x cubed plus x plus 3x squared plus 3, and then rearrange it so it's in a nice palatable form, x cubed plus 3x squared plus x plus 3. That'd be it.